Hello everyone, this is Ron Mertens from Metalgrass and MicroLED Info in the MicroLED Industrial Association. And I want to welcome you to the third session in our first MicroLED Connect live event, virtual event. And I think we have some really good speakers this time, as always. So I want to introduce Simon, from SmartKem, the UK-based developer of OTFT backplanes. And I'm going to give the stage to you, Simon. Let's begin.
My name's Simon Ogier, I'm CTO of SmartKem, and today I'm going to describe to you about our processes for making OTFT backplanes on top of micro LEDs as an alternative to the conventional way of attaching the LEDs to the backplanes. We're actually a US incorporated company, hence this legal notice at the beginning of my presentation. But actually, the majority of our operations are in the UK. They are based mainly in Manchester, where we have our semiconductor development at Blakely, North Manchester. So this is where the synthetic chemistry and formulation work is done, and some initial R&D. And then where we do all our device development and prototype development is up at the Centre for Process Innovation in Sedgefield. We do have an office in Taiwan where we do field applications engineering support and working with customers in Taiwan and other parts of Asia. So our materials are inks, which are coated from a solvent, and so they're very easy to apply to build up electronic devices. So they're both dielectric inks, planarizing inks, semiconductor inks, and surface treatments. And with that, then we can build up thin-film transistors in a very different way to the conventional PECVD sputtering processes. This shows the structure of an organic transistor, which looks quite similar to a lot of other transistors. Has 3 electrodes, source, drain, and gate, which are typically metals. And then there is a substrate, which can be either plastic or glass. And then the rest of the layers we develop as liquid coatable inks, which are either UV curable or just coatable and processed with hot plate baking to evaporate off the solvent. So we make a range of different materials, and they're all tailored in order to work together to provide a highly uniform, high performance transistor with very good stability. This shows some of the formulated inks that we supply, and we can supply in quantities up to say 1,000 litres per month or so, so we can support some quite significant prototype development, and they can come in a range of different pack sizes from 100 millilitres to 3.5 litres. At CPI, this is a CPI facility in the northeast of England, run by the Centre for Process Innovation, and this has a lot of prototyping tools that allow us to take the ink and to work out process routes for developing devices by thin film coating, photolithography, sputtering, wet and dry etching. And so therefore the inks can be imported into a pre-existing display line, which is used for say more silicon with fairly minimal changes to the process tool set. This just shows the process flow. It's using photolithography, masking and patterning, wet etching, dry etching, coating, UV curing, and other types of fairly standard processes that you would find in an amorphous silicon backplane. So we use a dual gate device. So it has 2 gates, a bottom gate and a top gate, mainly for exclusion of light from the transistor to stop it from changing its properties when under high illumination. So these 5 masks can be used to create the basic transistor stack with interconnects, but then you can apply other masks in order to convert it into different type of devices. And so we've done all of these types of devices like OLED, organic photodetectors, logic devices, as you can see here from this small cartoon of one of our substrate designs. And then today I'm going to talk more about the way in which we've used this process stack on top of mini and micro LED in order to make displays through the use of a planarizer with a patterned layer in it. And I'll show you some of these demonstrators later on. So the key feature of our materials is that they're basically they're processed, the semiconductors themselves are designed in the chemistry, and so the properties are determined by the chemical structure and not by any post-processing. The heating processes that are used are mainly just to evaporate the carrier solvent used to coat the liquid.